Good afternoon, everyone. So my name is Rajesh Vayavur, and I'm a research associate for the geophysics. And I will be presenting 3D potential field modeling and inversion of megalith transects. And Richard Smith will be presenting the second part of the presentation. He'll be presenting one of his PhD students' work. So these are the source of funding is mainly from Megalith, CFRF, and Merck, and then these are some of the software partners for this project. So these are a brief outline of the talk. So I will start with the introduction, and I will show some example on the Sudbury transect, and then I'll talk about the future work. So as you know, we have like 13 megalith transects. So for this presentation, I'm going to show some preliminary results from the Sudbury transect, and Richard and Fabio will be presenting on Matheson transect. So coming to the Sudbury area, so we all know the Sudbury structure formed because of the large meteorite impact around 1.87 billion years ago. So the current Sudbury structure lies exactly towards north on the Archean rocks and towards the south Huronian group of strata, which belongs to Paleoproterozoic age. So the Sudbury structure is mainly famous for nickel, copper, PG, sulfide ores deposits. So these deposits mainly occur along the rim of the SIC, Sudbury Igneous Complex, and some of the deposits form along the offset dikes. So our present study area for the Sudbury project is along the eastern part of the Sudbury Basin. And I also overlay the Vanapati crater. These also said to be a meteorite impact, which is a Eocene event. So I will give a brief overview of the project, Sudbury project. So in 2017, Metalith, in collaboration with Valley and Glencore, as part of NSEC grant, they collected seismic data along this transect in the eastern part of the Sudbury Basin. So they also collected MT and AMT data, and they also collected gravity data. So the main primary objective of this project is to study the shallow to deep crustal scale studies to understand the metal endowment in the eastern part of the Sudbury Basin. So the specific objectives for the potential field modeling is to create a 3D constrained geological model for the top 10 kilometers of the upper crust. So we already have a previous model, 3D model built by Olanian et al. In 2015. So why do we need a new model? So basically our area of interest lies here in the eastern part of the Sudbury Basin. And we have all the new data sets like seismic, MT, gravity. And so basically the previous model is built using 2.5D modelings along the lithoprobe cross sections. For this project, we're gonna deal everything in the 3-dimensional from the beginning. So this is a gravity dataset. We're gonna first of all we start with some smooth inversions on gravity and magnetic dataset. So this is the gravity dataset we are using. So the black dots represents the metalith stations, and the red dots represents the GSC stations. So this is a corresponding complete Boger anomaly grid. So this will be used for doing some smooth inversions. So this is the final density model after inverting the gravity data. So we used a VPMG algorithm for inverting this data set. The final RMS misfit for this final density model is 1 millicar. Coming to the magnetic dataset, so we used GSC regional compilation dataset, which is of 200-meter line spacing. So these, you can see clearly the magnetic character varies from the western part of the Sudbury Basin to the eastern part of the Sudbury Basin, where our metalith transect lies. So we will investigate this feature here in our presentation. So we also inverted the magnetic data using the same algorithm, and the final RMS speed for this magnetic final model is 7 nanotesla. And coming to the 3D density model, so we took a cross section along the metallurg transect profile, so that we can see a clear, smooth variation of the densities in the subsurface from south to north. If I overlay the geology on top of that, we can clearly see the Sudbury Basin is clearly delineated here. So if I import base of Sudbury Igneous Complex, so this is a 3D model surface from Valley and Glencore. So I imported that surface to see the correlation between the dip of the SIC surface with the density model there. So it's gradual dipping here. It matches with the SIC surface, and it's steeply dipping here. It matches with the density model here. So this is a 2D projection of the 3D cross section. So you can, if I overlay that 3D surface, base of SIC surface, model surface, we can see the 2D projection of that on the density model. And if I overlay some contours on the density model, you can observe some more features. Example, central uplift here. You can see something going on, which is central uplift. So this interpretations is consistent with the previous models, density models and geological models. The main feature from this model is deeper, high dense features here. So we will investigate these features in the presentation. And here to the south, there is a dense moderate to dense feature which represents a granular friend. So we will further investigate these features in the presentation. So starting the shallow anomalies investigation. So to understand the basin geometry, so we created a isosurface, density isosurface using a 0.06 gram per cc. So this is a isosurface created from that value. You can clearly see the Sudbury Basin is clearly delineated nicely here. And then the trough here, the trough represents the Huronian group of sediments. So we also have a high-resolution AMD dataset along the transect. Edamola performed some inversion on this AMD dataset. So I imported that model as an ISO volume. So I only used 1 to 100 ohm meters to see only the low resistivity anomalies. So there are three main low resistivity anomalies here, which have high number of cells. So I overlaid that thing on the density model to see the location of the low resistivity anomalies. So you can see that the low resistivity, the dip of this low resistivity anomaly matches with the density variation there. And this anomaly matches like dips towards the Huronian strata there. So if I overlay the model surface from Valley and Glencore, we can clearly see so that model surface cuts the low resistivity anomaly. So it may be like a contact or footfall type of deposits. We also have high resolution gravity gradometry dataset, which is provided by Valley and Glencore. So I'm only showing here a TZZ component of that gravity gradometry dataset. So if I overlay the low resistivity anomalies there, on top of that gravity gradometry, you can clearly see this low resistivity feature matches with the high density at the surface. And this low resistivity matches with the high densities at the surface. So coming to the deeper anomalies investigation. So I created an isosurface for this anomalies. So if you see this anomaly like projected towards the northeast direction. So if I see from the top view, so you can clearly see there is some kind of folding feature for this high dense feature. So if I overlay the susceptibility model from the magnetic inversion, you can clearly see the high dense feature matches with the high susceptibility there. And there is a discontinuity between the high susceptibility models. So if I make that transparent, you can see the inside there is a high dense feature which matches with the high susceptibility, and the high dense feature matches with the high susceptibility here. This is exactly the top view of the model. So you can clearly see that there is some folding kind of feature, high dense feature here, which matches with this high susceptibility feature here. And also I overlaid the horizontal derivative magnetic grid. So basically it can clearly delineate that like there is a uniform nature of this magnetic character for this western part of the Sudbury Basin. But here in the eastern part, you can clearly see there is um, a gap in the magnetic uh, um, anomaly here. And then if I make it transparent, so this high dense feature from the density model matches with the magnetic gap there. So the folding feature uh, matches with this magnetic gap there, and also this susceptibility discontinuity exactly matches this magnetic gap there. So if I overlay the regional faults on top of that model, so you can clearly see there is some like we know that there is a south range shear zone which is passing along this direction, which may have sheared this anomaly. Initially, maybe they are connected. Maybe they shared this anomaly towards the eastern side. So one of the possible interpretation might be because of this folding of this high dense features and the discontinuity in this magnetic susceptibility model. Um, um, Maybe like the Arkin mafic rocks may have altered the rocks, and then uh, it changed because of the alteration. Maybe change the magnetic character in the eastern part of the Sudbury Basin. So this is one part of like a basic preliminary interpretation. So this can be changed later, but so and also the Archean basement folding is already shown in some of the geological interpretations previously. So this might be like we can give a geophysical evidence of the folding features of the Archean basement rocks from this study. So I overlay some the mineral occurrences from OGS database. So we can see some mineral occurrences exactly at this magnetic gap there. So these deposits they're called as VMS type of deposits. We are not sure whether the deposits are have some deeper phenomena of this discontinuity here. But I just want to show the mineral occurrences there. So the future work is basically doing a detailed analysis along the seismic lines. These are the high process seismic data we have along the transects. So if I take example of line 182, so if I overlay the density model on top of the line 182, you can clearly see the variation of the dip of the reflections matches with the density model there. And where there is a truncation of the reflections, you can see there's clear gradient in the density model. And so if I overlay the susceptibility model on the top of the seismic section, you can clearly see the where there is a truncation of reflections. You can clearly see some gradient of in the magnetic model. So these are very basic interpretations, preliminary interpretations. So it might change in the as we include more data sets. So the final aim is to provide a 3D geological model of top 10 kilometers. But we start with the Valley and Glencoe 3D model. So they provided us like top 5 kilometers 3D model. So we will use that as initial model and then extrapolate that into the 10 kilometers and then do some unconstrained modeling. So finally, I would like to acknowledge Metalith team and Valley and Glencoe team who is working on this Sudbury project, and Brandon Smith for providing GS support, and Mira Geoscience for helping with the go-ahead. And that's it for the initial part of the presentation. I think Richard will take over from here. So I will stop sharing, Richard.
Okay, thanks very much, Rajesh. I have a little bit of time to talk about some of the work that Fabiano Della Justina has been doing. He's a PhD student, been with Metal Earth now for 3 years. He's originally from Brazil, where he did an undergraduate and a master's degree. And he's been doing some gravity inversions for the Matheson area and trying a couple of different ways of doing that. He's been trying inversion models with fixed and variable density values. So this is the Matheson area. On the left, we have the Metal Earth geology map from Mont Sign and others. But that's a little bit too complicated and too detailed for the work that Fabiano has been doing. So he has taken John Ayres' map, which is a little bit simpler, and done some further simplifications to classify the rocks on the basis of their physical properties. And these are the simplified geology that he's been using. So those are the geological constraints. The other constraint in his modeling is the gravity data, and you can see here the gravity data, which includes the Metal Earth data collected on the positions marked with blue, and the surrounding red dots are the government gravity data. And this is what the gravity data looks like once it's been gridded. So the idea is to use this gravity data and the geology and other information as well to divide up the Earth into a number of different cells, as you see here, 25 meters high, 100 meters by 100 meters, and to calculate the gravity response of these particular cells, starting, the host has asked me to start your video. Okay, start my video. Okay, is that okay?
Yep.
All right. So what we have here is an initial geological model, and you can see that the geology is known at surface. So the surface cells have been defined in terms of what their geology is. And then you can do an inversion of the gravity data, and the model will gradually be adjusted. So for example, the surface geology may be made to get a little bit deeper, and that will allow you to improve the fit between your measured data and your model data. So this is what the geometry inversion does. It changes the geometry of the model. So these are the simplified geology you see at the top, the different units, and we've specified the densities so that they lie within the ranges that corresponds to the densities that have actually been measured by these rocks. So we're taking into account the physical property constraints, in this case, densities. So for example, the Blake River group is generally around 2.9 grams per cubic centimeter, but can go up almost as large as 3.1 and down to about 2.75. And the other units are shown here. So that's another constraint. So the way Fabiano started off doing this was by doing two-dimensional modeling to try and understand what the geometry of the Porcupine was. So there were 5 different profiles where we had Metal Earth gravity data, and he modeled the geometry of the Porcupine on, just wait a minute. Sorry, I'm trying to get a laser pointer. On 5 different profiles. So there was one profile here, another profile here, another profile here, another one here, and a 5th one here. And you can see that when he was modeling that gravity data, he also took into account the seismic data that was available on the lines where seismic data was also collected. And the interpretation of the seismic was used here to work out what the base of the Porcupine assemblage might be. So in this case, that was the interpretation of the base of the Porcupine. So that's what was used in the 2D gravity modeling. So those 2D models you can see summarized here in 3 dimensions, and those were used to define the 3-dimensional shape of the Porcupine assemblage. And then this shape was put into the starting model of the 3D inversion. So the Porcupine assemblage was defined here in terms of its thicknesses and positions and dips, but the other geological assemblages were all specified only at surface, and then the inversion was used to work out what the deeper geometry of the other geological units were. So that's the starting model. And that starting model has a gravity response that looks like this, which doesn't look like what the actual observed data is. There's a difference, as we see here. And the idea of the inversion is to adjust the model until this difference here starts to look like it's nothing or zero, and the model data looks more like the observed data. And if it does look more like the observed data, then the misfit will decrease from a large value, ideally down to a value of 0 if there's no difference between the observed and the model data. But what happened is, when the inversion went, when the misfit was calculated, it went down and it got to a value of around 2 here, 2 milligauss misfit. And that was the best that could be achieved if, in this case, you fix the densities and allowed the geometry to move. So this is the case A that Fabiano looked at. Then once he got to this misfit here, about as low as it would go, he then allowed the densities to be changed until the misfit was a little better, but it wasn't much better. So there wasn't a significant improvement. So that's inversion type A. Inversion type B, he first allowed the densities to move, and then he allowed the geometry to change. And when they did that, he didn't get a very good reduction when the densities were changing. But then when the geometry changed, it did reduce. But you'll notice that it reduced only to a misfit of about 3 milligauss. So that approach didn't give as good a fit as approach A. And just to illustrate that, here we can see the calculated data compared with the observed data, and most of the features have been reproduced, as you see here. But in inversion B, the features aren't reproduced as well on the calculated data as they are on the observed data. So, for example, this feature up here isn't identified. Other differences are apparent if you look at the final model. So in inversion A, the features that were mapped go to much greater depth than they do in inversion B. So looking at the misfits, you might think this is probably a more realistic model. In both cases, the depth or thickness and geometry of the Porcupine was fixed, but if you don't fix it, the Porcupine goes down to great depth, 10 kilometers or so, and that's not considered to be geologically realistic. So that strategy was not persisted with. So some things that have been learned out of this modeling is that the depth of the Upper Tisdale is highly variable. The depth of the Blake River group thickens going from east to west, and the Waterberg batholith is thick, but it's quite variable with thick and thin sections. And the Kidd Munro that you see here is thin in some places, but thicker in other places. And the Porcupine had to be fixed, so we didn't really learn too much about the geometry of the Porcupine from the 3D inversion. So those are the conclusions to the talk, which is basically the things I've been talking about up until now. So are there any questions?
Thanks, Richard. There is a question from the chat room. Were metamorphic grades, green schist and fiblite considered in the gravity model? How were you constraining the gravity?
No, I'm not aware that the metamorphic grade was considered in the gravity model. We used the densities that were available, and I don't think the densities had a grade associated with them. They were just had an associated lithological classification.
Okay. Are there other questions from the audience? I got one, Richard. What's the scale? What's the vertical scale on those block models?
Yeah, you know, I'm not sure exactly, Russ. That question occurred to me, and if I asked Fabiano, then I forgot the answer, or maybe I forgot to ask him. Sorry about that.
Okay. There's another question in the chat. How did the inverted models compare with the seismic sections?
Yeah, that's a good question. So let's just go back and look at the seismic section. So the seismic section, up here, you can see it doesn't have a lot in it, and it's difficult to interpret. There's a lot of features in the seismic that look like there's some sort of migration artifact or something like that. And there is, I mean, this interpreted boundary here is not, you know, apparent. There's a feature down here, but there's not a lot in the seismic. The seismic data isn't necessarily that easy to interpret at Matheson.
Okay, good. Is there any other questions?
I have a question for Raj. One way that you might want to look at the interpretation of that central uplift for Sudbury is that it might also be offsets along faults, because there is major faults that are cutting through the south range of the Sudbury structures, and it might be. And I think Daly, this student that was with Richard, interpreted it. He had a similar features that he interpreted in terms of fault offsets. So that's something you might want to look at.
Yes, yeah. So yeah, the results I'm showing is basically very preliminary interpretations and preliminary results. So I'll be looking at all those models, previous models, for further interpretation. Yeah.
Yeah, and the east range, as far as I'm aware, like it's not more strongly sheared than any other parts of the submarine company. So it's quite high temperature metamorphic rock typically, and I haven't like mapped the east range, but the few field trip I've done there, the rock didn't appear to me to be strongly sheared.
Okay.
All right, good. Thanks.